Hello and welcome to the second of a two-part webinar introducing you to the basics of the Wolfram language. Last time we were talking about how to use notebooks, write functions and work with data. And this time we will look at how to visualize your results, how to make interactive applications and demonstrations from any expression, and some mathematical and statistical functionality. There are many different ways to make visualizations in the Wolfram language. We will begin with plot, a way to plot a function or set of functions. The basic syntax is this. So the first argument, f, is the function or a list of functions. The second argument is the variable to be plotted with respect to, and its range, minimum to maximum, in this case x. So for example, let's plot sin x with respect to x from 0 to 10. To plot more functions on the same axes, just add them in a list to the first argument, like this. There are many other plot functions with similar syntax. For example, parametric plots, when you want to plot functions based on some parameter, in this case t. Again, the first argument is the function to be plotted, or a list of functions to be plotted, while subsequent arguments are variable specifications. Nearly all of the visualization functions in Mathematica also have three-dimensional equivalents. In most cases, just add 3D after the usual name, such as plot 3D. Note that the syntax is very similar to the 2D case. There is just an additional variable specification. Similarly with parametric plots. Note that the outputs are interactive and can be rotated with the mouse, zoomed using Alt, click and drag, or panned using Shift, click and drag. If you have a set of data rather than an equation, you might need to use listplot to visualize it. Let's create some example data. Here we are taking the first 25 prime numbers. Then you just use listplot on that data. If you are using one-dimensional data, just a list of values, then listplot will assume that the x value is the position in the list. There are two ways to make the points join up. You can either use the expression list_line_plot, or you can use listplot and add an option called joined. If you set joined to true, this has the same effect. As seen above, if you simply provide a list of numbers, listplot assumes they are at unit intervals. You can also give two-dimensional data. Again, you can add 3D to the end to use 3D data. You can provide a two-dimensional array of height values to create an interpolated surface, or you can provide x, y and z values for each point. Here we are just creating some example data, then visualizing it. If you just want to view the points in 3D space, use list point plot 3D. When you are plotting data which is based on time, often you need special formatting or labelling. It is a lot easier to do that with specialised functions like dateListPlot. Here, we are plotting a list of values starting in August 2000 in a Gregorian calendar. The calendar can be changed. This is commonly used in financial visualization, but can be used for any time-related data. There are a variety of charting functions in the Wolfram language. They intelligently format the data to include tooltips and so on, so you get the best result possible with as little effort. Most charts can be used to visualize multiple data sets. Bar charts can be created easily by using bar chart on a list of data. You can visualize multiple data sets by adding more lists of data. Pie charts are similarly written. If you click on the slices of pie, they are interactive. Again, you can add more data sets to visualize them at the same time. If you have statistical data or a distribution, you can use a histogram to visualize it. Just use histogram on your list of data. In this example, we are using random variate to generate random data from a normal distribution. And don't forget, you can make all of these 3D by adding 3D after the usual name. For histogram 3D, you will need another dimension to your data. Graphs are a set of nodes joined by edges. They are easy to create and have a range of analysis functions. To create a graph, use the head graph, then provide a list of connections between nodes. To get the edge symbols, you enter escape, UE, escape, for an undirected edge, or escape, DE, escape, for a directed edge. Graph functionality has been largely expanded in version 10. There is now support for mixed graphs, with both directed and undirected edges, multigraphs, with multiple edges between the same two nodes, and 3D representation of graphs. There are many styling options, as with many of Mathematica's visualization functions. As well as visualizing graphs and networks, there are a range of analysis functions. For more information, go to the Graphs and Networks guide page in the documentation. You will often want to change how your visualization looks or behaves. You can do this using options. Here is a quick introduction to some of those options. You can read more on the Graphics Options and Styling guide page. First, you might want to change how much is shown of your plot. For this, you need to use Plot Range. You can use All or Full to show all of your data. If you want to show a specific range, the syntax is a list, where the first argument is a list x minimum to x maximum, and the second, a list y minimum to y maximum. If you want your data points to be scaled over a particular range, say 0 to 1, use data range. Here we are scaling data that is from 0 to 100 to be from 0 to 10 instead. One of the main options for customizing your visualization is plot style. It is an option to a visualization that can give a list of values to apply. For example, here we are modifying this plot to have a thick, red, dashed line. If you are plotting multiple functions, then the position in the list refers to which plot you are modifying. In this example, we add a nested list to apply 2 changes to the first plot. To modify a group of settings at once to a preset appearance, you can use Plot Theme. Plot Theme is an option with various possible values written as strings. Each can then be customized using plot style. Plot Theme is available for many visualizations, including charts. Often, you will want multiple visualizations on the same axes. To do this, use Show on all of the graphics you wish to combine. Coordinate system transforms are handled automatically. When you use Show, be careful which order you write your visualizations. Options are inherited from the first graphic you give to Show, and the graphics go from back to front in sequence. Show will allow options to be used on all of the plots. This may be necessary for situations where the plot range is different for different plots. Many Wolfram language expressions can be made interactive with the manipulate function. This is especially useful with visualization functions. For example, consider this basic plot. The manipulate function is written manipulate, then the first argument is the expression, and the following arguments are lists with the variable and the range it's being varied over, minimum to maximum. Let's try that on our plot. Here, we're just wrapping the plot with the manipulate function to enable interactivity. Manipulate automatically constructs a graphical user interface. There are many different ways of writing manipulate. If you add more lists of control specifications, you will get multiple controllers. You can have as many of these as you like. Manipulate can be used to make any expression interactive. Manipulate automatically chooses and labels controllers based on the input. For example, a discrete list of inputs might create a series of buttons instead of the slider seen previously. There are several possible default controllers. A long list of possible inputs will create a drop-down or pop-up menu. You can create a two-dimensional slider box by giving the start and end values for the variable as lists of length 2. If you would like a freeform input field, just put the variable in a list on its own or with a single starting value, in this case tan. Be careful with this, as a poor input can break the output. If you want to decide the control type yourself, you can use the control type option. There are a list of possible controllers on the control type documentation page. You can use control type on individual controllers, or you can set a default by using it on the entire manipulate. It is possible for the manipulate to have set values when it is evaluated by giving initialization values in the control specification. You do this by putting the variable in a list and following it with the initial value, like this. It is also possible to label each controller with an arbitrary expression. To do this, you need to have an initialization value to avoid ambiguity, then add the label into the list, like this. Here are some more useful hints for when creating manipulates. There isn't time in this session to discuss them in detail, but you can find out more in the Advanced Manipulate Functionality guide page. The Wolfram language uses arbitrary precision and has 3 different ways of using precision when working with numbers. The first is exact precision, perfect representations of the numbers. Exact precision is good because there are no errors, but bad because it takes more space on the computer. See how complicated this calculation becomes after only 2 iterations with exact precision. To get the decimal approximation to an exact result like this, use n. The second is machine precision. Because of the way decimals are stored in a computer, there will always be some small precision errors. It depends on the operating system of your computer, but usually this will be 16 significant figures of precision. You can find out what the value is on your system by evaluating $machine precision. Machine precision is significantly faster and more memory efficient than exact precision, but in certain cases it can quickly build up large errors. High precision is a great middle ground. It lets you decide how many significant figures of precision you would like. You do this using set precision. All of these types of precision have their own advantages and disadvantages, and you should decide which is appropriate based on the problem you are solving. The Wolfram language has native support of algebraic manipulation, which allows users to operate directly on mathematical expressions. Here is an example polynomial to work with. We can expand out products and positive integer powers in our polynomial using expand. Then we can obtain the coefficients of a given term using coefficients. They are given in order of lowest power to highest power term. And then factor the polynomial back into its original form with factor. There are many more operations available on the algebraic manipulation guide page, including modulo primes, complex numbers, piecewise functions, and many more. The Wolfram language has various built-in functions for simplifying mathematical expressions, the most common of which is simplify. Simplify performs a sequence of algebraic transformations on an expression and returns the simplest form it finds. Let's try taking the derivative of a rational function to create a complex polynomial. Then we can try and simplify the results. You can see that the expression has been factored, so it is a multiplication of a rational term and a longer polynomial. You could have the same effect in this case by using together. Together combines as many of the rational terms in an expression as possible, in this case putting it in its simplest form. Another example of a fundamental theorem of calculus is that if you integrate a polynomial, then differentiate it again, the result will be the original polynomial. To start with, this does not appear to be the case, but if we simplify the result, it returns to its original form. Full simplify tries a wider range of transformations on the expression involving elementary and special functions, and returns the simplest form it finds. In some cases, simplify may not have the transformations available to do a good job, but full simplify will. For example, with gamma functions x gamma x is equivalent to gamma 1 plus x, but simplify does not have the transformation available, so does not simplify the expression. Full simplify and simplify assume the most general situations. They do not make any assumptions about the symbols. In this situation, you can use the option Assumptions. This allows you to constrain the results so a more simple result can be returned. For example, the square root of x squared could be minus x or plus x, but if we assume that x is below 0, we get the more trivial solution minus x. Complexity function is an option for full simplify and simplify that gives a function to rank the complexity of different forms of an expression. This means you can create your own function to decide which properties of the expression should add to the complexity. The default behavior of simplify is to count the number of sub-expressions and the number of digits in integers. In the example below, leaf count refers to the number of sub-expressions, and count is checking for the head tan anywhere in the expression. So here we get a differently simplified expression, assuming that tan is less simple. The Wolfram language includes a number of functions for solving equations and inequalities that use the same structure. Solve is the main solving function. It is a symbolic function, so we'll use symbolic methods. The system of algebraic equations to be solved is provided as a list in the first argument, and the variables they depend on are specified as the second argument. A system of inequalities can also be solved in a very similar way. There may need to be an extra argument specifying what domain the inequalities should be solved over. The result is likely to include conditional expressions, meaning a result that relies on some condition. The output of solve is given in a list of rules. Rules, a right-hand arrow, are used to transform the left-hand side into the right-hand side. We can use replace all /full stop to turn all of the variables, such as x, in the expression into the value given in the solution. Usually, there are multiple solutions, so you will need to use part to select which solution to use. In this case, we are using the first solution. For some systems of equations, solve will not be able to find a reasonable solution. Reduce has more methods available and so can provide better solutions in some cases. In this example, x plus e to the x equals a half. With this expression, solve produces warnings that solve may not be the best answer. When reduce is used, it will often give a list of possible solutions separated by the or symbol, 2 bars. Some of the solutions may have conditions, such as the first solution in this example. The first part is a is not equal to 0 and the solution, meaning that the condition a is not 0 has been put on that solution. When solving a system of equations, sometimes symbolic methods are not possible or not appropriate. You will then need to use numerical methods. The Wolfram language has 2 main numerical solvers, ndsolve and findRoot. ndsolve tries to find numerical approximations to the solution of the system and may produce many results. In this case, the solutions are complex and can be visualized on a complex plane by plotting the real part, re, and imaginary part, im, and substituting in those roots. It is possible to constrain the search to the set of reals by adding another argument. findRoot is slightly different in that it searches for one solution starting at a given point. It is possible to find the root for more than one variable at a time by adding to the variable list in the second argument. Calculus in the Wolfram language is performed through a small number of highly automated functions, as is the solution of differential equations. Differentiation is done using a capital D. Note that this is one of the few expressions in the Wolfram language that does not use a full word. It is written with the first argument being the expression to differentiate, then after that, a list of which variables to differentiate with respect to and how many times. In this first example, we are finding the first derivative with respect to x. In this second example, we are differentiating with respect to x once and y twice. Note that the result uses prime notation, read as the second derivative of g. Symbolic integration is written as integrate, and again, the first argument is the expression to integrate, and the second argument is which variable it is being integrated with respect to. If you want to perform a definite integral, integrate over a range, add the start and end points in a list with the variable. To optimize an equation with respect to a variable, you can use minimize or maximize to minimize or maximize a function with respect to the specified variables, to find the global minimum or maximum of the function. It also has the ability to generate conditional solutions. To use numerical methods for integration, use nintegrate. It is written in the same way as integrate, but requires a range to integrate over. Similarly, numerical optimization is done using nminimize or nmaximize. Find minimum and find maximum are similar, but search for a local minimum or maximum starting at a given point. dsolve finds symbolic solutions to differential equations. It can handle ordinary differential equations, certain classes of partial differential equations, and differential algebraic equations. An example of dsolve being used is in solving a damped oscillator. The system of equations is as follows. x-t refers to dx dt, or the velocity of the oscillator, and v-t refers to dv dt, or the acceleration of the oscillator. X of 0 and v of 0 are the initial conditions, the starting position and velocity of the oscillator. Solve gives the solutions to the system in the format of a rule. The left-hand side of the rule is the name of the function, in this case x and v, and the right-hand side is the pure function that describes its behaviour according to the provided equations. These functions can then be plotted by using replace all or /. If the system is based on some parameter, in this case t, you can use parametric plot. It is possible to not give initial conditions and get a general solution that contains constants, c of n. ndsolve is a general numerical differential equation solver. It can handle a wide range of ordinary differential equations, ODEs, as well as certain partial differential equations, PDEs. ndsolve is written very similarly to dsolve, but a range for the independent variable must be specified. To solve a set of ordinary differential equations, the first argument is the system of equations, the second argument is a list of functions to solve for, and the third argument is the independent variable specification. In this example, we will solve a Lorentz system, a simplified model of atmospheric convection. First, set up the list of differential equations and initial conditions. Then, we use ndsolve with those equations to solve for x, y, and z, and then give a range for our independent variable t, in this case 0 to 200. Then, the solution can be visualized using parametric plot 3D. To solve a set of partial differential equations, add another variable specification as an extra argument. In this example, we are solving a set of exactly solvable PDEs, the KdV equation, which is a mathematical model of waves on shallow water surfaces. Again, the first argument is the full list of differential equations and initial conditions. The second argument is the function we are solving for, and the final arguments are the independent variables and their ranges. Here, the method stiffness switching has also been used, which automatically adjusts the step size of the numerical solver for a better result. This solution may take some time to complete. By using Manipulate, the wave collision can be visualized interactively. In addition to symbolic math, Mathematica has a large numerical suite of functions built into it. A seemingly simple function, which is in fact quite complex, is n. N is used to force a numerical approximation to an exact number. You have seen several numerical functions so far, including ndsolve. Note that there is a difference between using ndsolve and using n on the result of a solve function. Solve will always use the symbolic approach, and then n will take the result of that and make a numerical approximation, whereas ndsolve will first try the symbolic approach, and if that does not give a satisfactory result, we'll then use numerical methods. Finally, let's look at some statistical functionality. To begin with, let's generate random numbers and perform calculations from a given distribution. To do this, we will use the distributed symbol. Distributed asserts that x is a random variable that satisfies a normal distribution with mean, mu, and standard deviation, sigma. The symbol could be entered escape, dist, escape in a notebook. Once this dist has been created, we can use the assertion to do probability and expectation calculations. In these, notice that we are using the symbols mu and sigma, so all of the calculations are symbolic rather than numeric. It is also possible to generate random numbers from a distribution. By using random variate, it is possible to generate a set of numbers from the distribution given in the first argument. In this example, 20 numbers from a uniform distribution between 0 and 1 are being generated. There is a wide variety of built-in distributions, both discrete and continuous, to be chosen in the Wolfram language. They can be used both numerically and symbolically. Now, let's look at some descriptive statistics of data. First, some test data needs to be generated using random variate. Then, we can look at some of the statistics of that data. Here, we are taking some averages, the mean and the median. Then the variance, that is, how spread the data is. Its skewness, whether the data is symmetrical or not. And the kurtosis, how spread the tails are compared to how spread the peak is. Finally, we could create a visualization from that. For example, we could plot the cumulative density function of the data. Here, an empirical distribution is a distribution that represents the data points in a distribution format. Hypothesis tests can be automated in the Wolfram language. To fit a distribution to a set of data, use distribution fit test. The first argument is the data to fit to. With no other arguments, this would test if the data is normally distributed. The second argument is the distribution to test against. Here, automatic is being used, so the distribution will be chosen automatically. By giving a third argument of hypothesis test data, it is possible to create a hypothesis test data object that can then be used to access more information about the fit. Now, different information about that fit to the data can be accessed, such as the test data table and an automatically generated test conclusion, describing the null hypothesis, the result, the distribution that was tested against, the p-value, and which test was used. Built into the Wolfram language are linear and nonlinear fitting functions. Models can be given directly in symbolic form. The Wolfram language also supports interpolating functions that can be used throughout the system to represent approximate numerical functions. To fit a linear model, you can use linear model fit. It is fairly simple to use. The first argument is the data. The second is a list of functions that will be linearly combined, and the last argument is the variables that these functions use. The output will be a fitted model object, which can also provide other information about the fit, such as a function to plot. Nonlinear model fitting is similarly written. It may be a little slower for more complex fits, but it can fit more complex models. The first argument is the data, the second is the basis model, the third is the list of parameters that will be optimized, and the last is the variables that the functions use. And again, the result is a fitted model object that can be used to examine the fit in more detail. If you want to just extract the basic symbolic form of the fitted function, use normal. Normal takes away all of the formatting and extra details of an object and just leaves the raw form. As you have seen, both linear and non-linear model fits create fitted model objects that contain more information. You can access this information by using the model like a function on the name of the property you are trying to access. There are many more properties that can be seen in the documentation for linear model fit and non-linear model fit. This was the second of a two-part webinar teaching you the basics of the Wolfram language. In the first part, we talked about a brief introduction, how to use your notebooks, how to create some functions, and finally how to deal with data. And this time, we discussed how to create visualizations from your computations, how to make interactive applications from any expression, and then some mathematical and statistical functionality. That's it for this series of webinars. I hope you've enjoyed learning about the Wolfram language. We have many other training courses available at wolfram.com/training, many of which are free and on demand. If you are already comfortable with code and would like a more fast-paced course, there is a fast introduction for programmers here. For a message forum where you can ask other Wolfram language users for help, go to the Wolfram community at community.wolfram.com or the Mathematica Stack Exchange page at mathematica.stackexchange.com.